Got everything up and running. Recorder's on. All right, so we are going to continue from our previous discussion. So let me go back and retrieve all that good stuff. Binomial distribution, we were talking about that last time. All right, so we are now moving on from this kind of awful mess, which is the proof by induction of the binomial theorem. So we are now moving on to this little single term here, which is basically saying if you have n items, okay, you have n coin tosses, and you want m of those to have heads. P is the probability of landing on a head. Q is the probability of landing on the tail. This will give you the probability of exactly that. Okay, so this is a really important um, formula. Okay, because it gives you the probability of the having n events of which m of those are a particular kind, and p is the probability of the particular kind that you want. So that's kind of the way it works out. So let's go ahead and see if we can apply that in um, maybe an exercise. Okay, so let me just write out the scenario, and then you guys can tell me how to approach that. So let me go to my trusty mouse pad. Mouse pad, come on. Accessory mouse pad. There we go. All right. So we can erase that. There we go. Put it here. So I'm going to give myself a problem. Okay. So we are going to say that there are 6 coin toss events, and the chances of 3 heads out of 6, or 3 of the tosses end up on heads, is on the average. Okay, so after observing lots and lots of experiments, each experiment has 6 tosses, and the chances of landing on three of those 6 tosses landing on the head is, I'm just going to give it a particular number, is zero point 0.6 instead of what you would expect, which is zero point 0.5. Let me turn off a line number so it's easier to read. So the question now, okay, the question is, what is the probability of landing on a head in a single coin toss? Okay, so let's just say that is the question. How do we approach this and how do we answer this question? All right, ideas, anything. Okay, so if this is the exam question, what are you gonna do? But how? Okay, so tell me how you're gonna map the values into the binomial theorem. So we have the binomial theorem here. Okay, this is binomial distribution, and this is the binomial theorem up here. So how do we plug that in? Okay, first of all, which n are we talking about? What is n? See, the binomial theorem works for any n that's a natural number, and what we're looking at is a very specific n. So n equals to 6. Okay, so good, good. Okay, so there are a few good things coming from the discussion. So we know n is 6, but before we do that, we also know that somehow the binomial theorem seems to be useful. Okay, so we go by definitions. Okay, so now we have these two, and then what is the next step? What else? How else are we gonna plug in, what we have here? So 6 coin tosses, the chances of 3 head is zero point 0.6. 3 heads out of 6 tosses is zero point 0.6. The question is, what is the probability of landing on a head in a single coin toss? And I am just going to say this probability of landing on the head in a single coin toss, we'll just call that P. Call that P. Okay. So this way, I can just refer to the variable name instead of repeating that long sentence every single time. Okay, so now what do we do? The theorem itself is not going to be particularly helpful because the theorem says p plus q to the power of 6, okay, to the power of 6 is, okay, so we can do all the calculations. Um, 6 choose 0 is going to be a 1. So we are going to have, p times, p to the power, p is to the power of 6. And then, we have 6 choose 1, which is the next one. So what is 6 choose 1? The clock is ticking. So how many ways can I choose one item? Ordering is not important. Out of 6 items, that is a very intuitive question that can be answered in a few seconds. I got 6 marbles in a bag, individually labeled. How many ways can I take one marble out of the bag? No. You take let's label the marbles A, B, C, D, E, F. Okay. The first time I can pick a marble out. Oh, it is A. What is another possibility? Oh, it is B. It is C, D, E, F. So there are 6 possibilities. You can also plug it in based on the binomial theorem. Let me point to the screen. We're basically asking what happens when I equals to 1. When I equals to 1, it is n choose 1, which is 6 choose 1 in this case. So how do you compute 6 choose 1? Let's just say the intuitive approach does not work. Then what do? Throw our hands up and go like, okay, I give up. Exactly. So we go by the definition again. So are you guys starting to see the importance of definitions? Okay. So what are you going to do in the next exam, which is Wednesday, and also in the final exam? Make sure you have all the definitions on the paper that you're bringing to the test. Okay. It is open book and open notes. There is absolutely no excuse that people do not have the definitions with them on the day of the exam. Okay. But I am a little concerned because I might forget to bring that all those paper with me on the day of the second exam or the final exam. Put it in your backpack now. Whenever you work on something and you think I might be using this in text class, put it into the backpack and don't take it out ever. Okay? Because how much does a single piece of paper weigh? Not too much. Okay? But it gives you the reassurance that you will have it available. Okay? All right. So once again, 6 choose 1 is just 6. So we're going to say, all right, so we have 6 of what? P to the power of 5 times Q to the power of 1, but I'll just kind of make it easy to read. What about the next one? I equals to 2. So 6 choose 2. How do we compute 6 choose 2? 6 factorial divided by 2 factorial times 4 factorial. Okay, so can you figure out 4 factorial in your head? That's an easy one. What is 4 factorial? 4 times 3 times 2. I mean, times 1, yes, technically times 1, but times 1 doesn't do a single thing, right? 4 times 3 times 2 is 12, okay? So I can work on this on the side. 6 factorial is going to be the numerator for all of these, so might as well get it over with. So what is 6 factorial? If we already know 4 factorial is 12, so what is 6 factorial? How does 6 factorial relate to 4 factorial? 4 factorial is, yes, you're correct. Sorry, 24. So thank you. So what is 6 factorial? What is missing in 6 factorial when we already know what is 4 factorial? Yep. 6 times 5 times, and then the 120. So that is what? Can you do this without a calculator? 6 times 5 times 120. Hmm? It's 24, sorry. I just gave you the answer, damn it. No, 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 it's not quite that either, okay? It's 720. Yep, it is 720. Okay, so how do we compute, 6 choose 2? So 6 choose 2 is 6 factorial divided by the product of 2 factorial times 4 factorial. So what is that? It's 720 divided by, what is 2 factorial? 2 factorial is 2. Very good. 4 factorial, we just did it. Okay, I made a mistake. It is 24. So because it's 4 times 3, which is 12, and then times 2, which is 24. So now we just do this division. So 720 divided by 48. What is that? I need my calculator. No, you don't. Yep. So it is 15. So you can do it by hand, okay? I hope you guys still remember how to do the long division by hand because I don't want to hear anyone saying, I don't have my calculator with me, I cannot do this calculation. Yes, you can. Okay, so we have what, 720 divided by 48, okay? So there's 148 here. You subtract 72, you subtract 48 from 72. There's a 4 here, there's a 2 here, 240. That's an easy one. So it is in fact 15. All right, so where do we put the 15? 15 goes here. It is the coefficient times p to the power of what, 4? Wait, yep, it is 4. So it p to the power of 4 times q to the power of 2, right? What about the next one? The next one is when I equals to 3, which is the one that we want, okay? So what is that? What does it look like? So it would be 6 choose 3, right? So 6 choose 3. What is 6 choose 3? It's 6 factorial divided by 3 factorial times 3 factorial. Okay, what is it? What is that? 720 divided by, what is 3 factorial? It's 6, right? Okay, because it's 3 times 2 times 1, which is 6. We have 6 times 6 over here, which is 36. So we have 720 divided by 36. That should be a relatively easy one. 20, very good. So we have 20 of what? Okay, 20 is the coefficient of p to the power of 3 times q to the power of 3. Are we still doing okay so far? And then now we have, this is the maxed out coefficient. So on the other side, it's just a mirror image of everything that we have seen already. So if we expand the entire thing, it is going to be plus, 15 of p to the power of 2 times q to the power of 4, and then plus, 6 times q to the power p to the power of 1 time, which is just p, and then q to the power of 5, and then plus 1 of q to the power of 6. Okay, so that's how p plus q to the power of 6 is going to expand. So what is p? P is what we're looking for, which is the probability of a coin landing on the head in a single toss. Okay, then what is q? What do you think q is representing? The tail, okay, the probability of landing on the tail. So you go like, oh, okay, so we now know how the p and q are defined. P is the answer that we want. Q is 1 minus p, okay? And then some of you will go like, oh, we are just gonna go back to square one. All this is saying is this entire thing equals to 1. Yep, that is true. Because this is representing all the possibilities of flipping a coin exactly 6 times. Okay? What are the chances all six times we are landing on the head? All six times we are um, landing on the tail. Out of six times, one is a head, five of those are tails, and so on. So when you add up all of these, obviously it has to add up to one. It also makes sense on the other side of the equality because Q is 1 minus P. So what is P plus 1 minus P? That's just 1. 1 to the power of 6 is still 1. So everything still makes sense, okay? But we are singling out one of these to figure out something. We are singling out the one that is representing, what if, we from observation that three out of six tosses, the probability of an experiment ending up with three heads and three tails out of six coin flips is exactly zero point 0.6. So what we now have given, what we know is zero point 0.6 equals to just this term in the middle. Okay, this is the term that we are trying to figure out. Okay, is that okay so far? So now we have to solve for this. Okay, so we have q being 1 minus p. So this is the furthest we need to get in order to say, okay, we have one unknown and then we have everything else known. We should be able to solve for that p. But that's all we need to do, okay? Because just to solve for this, how would you solve for this? Hmm? That's Q. That's how Q is defined. Because Q is representing the chances of landing on the tail, so it has to be one minus the probability of landing on the head. So now we can solve for P. I don't need you to use algebra to solve this. If you get to this particular form, it is good enough. Because to actually solve with P, it's actually a little bit on the hairy side because you end up with P cubed, you have P squared and also P and then a constant to deal with. So it's not exactly an easy one to solve for. Spreadsheets can do that though. Okay. So are we good with this one, the solution of this? Okay. All right. So we are going to look at another example. This one has to do with an ancient technology called CDs or compact discs. Ask your parent or grandparent about it, okay? Because I think some of your grandparents might have owned a few CDs. Sorry? You have some CDs? Oh, okay. Hey, some grandparents are relatively young, okay? So I can see how some grandparents can have CDs. Let's do the math here, okay? So my current car has a cassette player. That is not. Yes. you have you they make Bluetooth receivers or transceivers that looks like a cassette tape. You just pop it into a cassette tape player, and now you have instant Bluetooth connectivity. Yep, yep. I remember those days. All right. So, what does this class have anything to do with CDs? It is a technology that we call oversampling. Okay, so let's check out what is oversampling. So we'll put a separator here, okay, and then we'll say the error rate of reading a bit correctly is, let's just say it is horrendous. Okay, it's zero point 0.2, which is 20%. So 20% of the time, your CD player is going to read a 0 or 1 incorrectly. Okay, that is really bad. Okay, so what do we do to fix this problem? We use oversampling. Okay, so we're going to use oversampling to try to fix this problem. So the solution is to quote unquote oversample. So we're gonna take a look at oversampling by 10 times. Okay, we'll just say it is a 10-time oversampling as a solution. So what does that mean? That means we are, as the disk is spinning, okay, we are reading the same bit position 10 times. Okay, if out of the 10 is actually not a good number, let's make it 9, because with 10 you can have 5 and 5 and then you're still undecided. With 9, because it's an odd number, you know it has to be a split that is not even. Okay, because the closest you can get to an even split is 4 5 or 5 4. Is that okay? Are we good? Are we doing okay so far with the math? Okay, so the solution is to oversample by 9 times. Okay, so we're going to read the same bit position 9 times, and whoever has the majority wins. Does that make sense? Okay, so we're going to say, all right. So that means, um, so we want to know, if we do the oversampling, what are the chances that I'm still reading the wrong bit or coming to the conclusion of the wrong bit? That's basically what we are asking. Do we all understand what the question is asking? I'm reading a bit, okay? If I read a bit only by itself, there's an 80% chance that I will read it correctly, but there's also a 20% chance that I will read it incorrectly. So if you're playing a CD, okay, your music is not gonna play, okay? It's just too bad, and there's not enough data to play any music, not even skipping. It's just not gonna play. So I want to fix this by oversampling. In other words, I'm reading the same bit over and over 9 times. Okay. Out of the 9 times, if there are more ones than zeros, I count it as a one. If there are more zeros than ones, I count it as a zero. So that's kind of what I'm doing. Okay. But we don't even need to know about the one versus the zero. All we care about is how many times is reading correctly and how many times is reading incorrectly. Okay, so in this case, I prefer p to be zero point 0.8, which is the chances of reading something correctly. Okay, is the chances of reading a bit once and it is correctly. So q is going to be the zero point 0.2. Okay, so now the question is, how is the binomial theorem going to help me? Okay, so we can expand out the binomial theorem, and in this case, it's going to be a little bit more of a problem, okay, because it just looks kind of long. So instead of doing that, we are going to use a spreadsheet. And yes, I can use a spreadsheet to do just about anything, including in the role of an assembler. All right, so we'll go ahead and 2025 1110. Okay, so we are going to work that out. Okay, so we are looking at um, the five, let's see, 10 numbers that we're dealing with here. So the 10 coefficients that we're dealing with, starting with the first one, is combin. Okay, we have 9, and we want to choose basically the row number -1, which is exactly how I would put it. So this way I can be super duper lazy and just kind of do it like this. Okay, and now we have all the coefficients. Are we doing okay so far? Okay. And I am going to also introduce how many p, or is the power of the p versus the power to the q. So I need to insert one row above, which is going to break my equation. That's okay. It's easy to fix. Just subtract one more. So these are the coefficients, and we take this out. Let me see, is that correct? 1, 2, 3, 4, 5, 6, 7, 8, 9. Somehow it's lopsided. There's a 9 missing. Right. Okay, because I forgot to do this. There we go. Okay, now it makes sense. So this is the coefficient of each term, and we now want to look at the power of p. So the power of p starts with 9, and then it decrements as we move down the list. So this one is going to be, the starting point, which is a 9. This one is just the 9 minus the 1, and we can use the same equation to go all the way down to the last one. And then the power of q is exactly the opposite. There are several ways to do this. I think the easiest way is just to say it is 9 minus the one thing, the one cell next to it. So there we go. So instead of writing out the equation in a very horrendous way, now I have a fairly nice representation of the expanded out version of the whole thing. Are we doing okay so far? Okay. So what do we want to figure out? Okay. So we already know what P is. We also know what exactly what Q is. So now I can multiply, the coefficient with, P to the power of 9 times, Q to the power of 0. Okay, and I will put the product on this side. So I'm basically just multiplying the coefficient times P, which is zero point 0.8 to the power of whatever this cell is specifying, times zero point 0.2 to the power of whatever this cell is, specifying. That becomes the product of a particular term of the 10-term expanded form of P plus Q to the power of 9 in this case. Is that making any sense? Let me just click on the formula so you can see it again. Are we doing okay so far? In fact, if I double click it, I think it color codes. Yep, that is nice. So are we good so far? I'm basically expressing a binomial expansion, but in a table inside the spreadsheet. Okay, so with that done, I'm just going to drag this down. And now we have, a whole bunch of probability. And you can see how it is kind of lopsided. It is lopsided because the chances of reading something correctly is zero point 0.8. The chances of reading something incorrectly is 0.2, and that's why it is lopsided. All right, so we're going to say if the majority of the bits are read correctly, then the whole thing is going to be read correctly. Is that making any sense? Okay, so what does that mean? That means if I read 9 times and all 9 times is reading correctly, obviously it is good. Okay, the interpretation is going to be correct. If I read 8 times and out of nine, excuse me, if I read 9 times, out of 8 times is reading correctly, and I make that conclusion, it's going to be the right conclusion. Okay, 7, 6, 5, they're all going to be correct. If I read 9 times and only four are, indicating the correct result, that's not going to be one of the correct answers. So what I need to do is to add up these particular values, because, this is the combined probability of this portion is going to be, if I just count the majority of the bits, and if I make a conclusion out of the majority of the samples, then the summation of all of these probability means I will come to the correct outcome, come to the correct interpretation. So let's see, what that number turns out to be. Okay, so uh, this is just a summation over these terms. Okay, because that's having the correct readout as the majority. So that turns out to be 0.98. Our per bit error rate is dropping from 20% down to a little bit less than 2%. Is that okay? So that's what oversampling can buy you, is if you already know for each sample, for each time you read something, the probability is like, that's not so good. You can oversample, assuming the distribution is even, like it's a predictable, then you can actually make it much better like that. So that's oversampling is an application of the binomial theorem. I mean, still doing okay so far? Okay. So that's kind of how we apply the binomial distribution for. Do we have any questions at this point? No questions? Well, a spreadsheet just makes it easier. But if you look at the math, none of the math is super duper hard. I mean, maybe the combination is a little bit more involved because this one does go to 9 factorial. So most calculators, have a factorial function. So with a calculator, this kind of math is totally doable. Yep. All right. Any questions? No questions? This is the equation. Mm? So if you want to look at what is A2, this is how A2 is done. So it's 9 0 for this one, 9 1, 9 2, 9 3, 9 4, 5 6 7 8 9 itself. Yep. I mean, the spreadsheet is readable to everybody, and you have a laptop. You can actually go onto the spreadsheet right now if you want to. Yeah, it's in the shared folder for this class, and it has today's date on it. In my assembly programming class, I typically get people to view the spreadsheet on the day, like kind of like right away. People just kind of sign in and take a look right away. All right. So are we still doing okay so far with the probability stuff? Okay. Mm-hmm. No, the objective of this exercise, this particular one, is to figure out what is the effective error rate if I oversample 9 times. And turns out the error rate is down to 1 minus the 0.9804, which is less than 2%. We started off with 20% as the error rate, and we are now down to a little less than 2%, which is still really bad. Okay, you still cannot play any music out of the whole thing, but it is much better. And the 20% error rate is really unrealistically high, so it's just a number that I pull out of thin air. All right. Any other questions? No? Okay. Um, so without any questions with probabilities, I mean, the binomial distribution was the last topic in this particular discussion because there's really nothing, not much after this. It's really just observe the empirical probabilities, which is kind of what we just did. Okay, we just kind of talked about it. All right. So with this done, I'll give you guys a choice because I think there are some topics that are independent. There is no interdependency. So let me show you what you can choose from. We can talk about the big O notation, which is actually big. Uh, it's more like a big theta notation. Okay, we can talk about that. We can also talk about graph um, algorithms. So there are two algorithms that can help find the shortest path. One is called Dijkstra's algorithm. The other one is called the A-star algorithm. So we can talk about those algorithms, or we can also talk about predicate calculus, which is sort of an expansion on propositional calculus. Propositional calculus cannot handle quantifiers. It just doesn't know anything about quantifiers. But predicate calculus can handle quantifiers. And the nice thing or the fun part of using predicate calculus is we have a programming language called Prolog that actually is the implementation of predicate calculus in a way that you can run, that you can actually get results out of. So that's basically what predicate calculus is about. So it's your choice. Okay, we have to cover graph algorithms. I think that one is kind of essential. Predicate calculus is kind of like it's fun to kind of talk about, but at the end of the day, maybe not really practical. And then the other one, which is a big O, big omega, and big theta, this one is kind of important for upper division classes that you guys will get into. So kind of your choice. Just go with the order. Okay, let's do that. All right. So a few terms to define. This one is kind of It's a little bit long with a lot of symbols and mathematical terms and stuff like that. But some of the mathematical terms are actually useful, later on in many of the other classes too. So I think it is good to kind of have some exposure early on. So we'll go ahead and start to talk about the algorithm time complexity, okay? Because there are multiple complexity when it comes to algorithms. One is time and the other one is space. In other words, if your problem doubles, okay, if the size of the problem doubles, how much RAM does it need? Is it going to be doubling or is it quadrupling or what? The other one is time complexity. Okay, if the problem size doubles, does it take twice as long to solve the problem? Does it take four times as long to solve the problem, or what? So time complexity is the focus of this discussion, but the entire discussion, if you look at the whole thing, it really can be applied to space complexity as well as time complexity, because we are really just talking about the symbols, what big O or big omicron is really representing. So we'll start with a simple example of this particular algorithm. It is kind of existing outside of a C function because I just want to illustrate the algorithm itself. So when you look at this algorithm, how much time does it take to complete the algorithm? That's the question, okay? So what we'll do is we're going to break it up into a bunch of stuff, okay? So the way we break it up is we identify how many times we have to go through certain parts of the calculation. So it is kind of obvious that these two will go through exactly n times. In other words, for every single element in the array, these two lines of code will have to execute. So that's going to go through exactly n times. Okay. This condition here will take n plus 1 times. Okay, there will be n plus 1 times that we have to evaluate this condition. Why? Why is there a plus 1? Hmm? That is correct. Okay, but why does it end with n? Yes, that's right. You need the extra one to fail in order to exit the loop. Okay, so that's the plus 1. Okay, and then the rest is just once, right? The initialization code here only executes exactly once, okay? So the way I, kind of, specify that is T1 is representing what? So T1 is for the initialization, that's for T1. T2 is the time it takes for one evaluation of this condition. And then T3 would be the time that it takes to execute these two statements over here. So are we doing okay so far? What T1, T3 are representing. So the T2 is actually multiplied by n plus 1, but I decide to pull the plus 1 and the plus 1 outside of the n to become its own term. So this way, T1 plus T2 can be seen as one single constant, and then the other constant is going to be T2 plus T3. So this will give us the exact amount of time that it takes for this algorithm to conclude, assuming that we know what is T1, T2, and T3. Are we doing okay so far? Okay, question? So we'll talk about that, okay? So right now, f of n is not a time complexity, but well, I take it back. So f of n is not an order of magnitude. F of n is the exact amount of time it takes for this algorithm to execute. Okay, are we good so far? All right. So f of n is not an approximation. It is the exact amount of time that it takes in order to solve a problem of size n in this case. So there are more complicated algorithms, and I'm not sure that I want to go through the exact detail. So if you look at bubble sort has a time complexity of something like this. Okay, There's the initialization, things that we only execute exactly once. We'll pull all of those into T1. There are things that we only execute n times. We'll pull all those into T2. And then there are things that we have to do n squared times. We'll pull all of those into T3. So, we are not going to go through the exact, complexity of the exact makeup of T1, T2, and T3, but we can just say that there exists T1, T2, and T3 such that the amount of time it takes for a bubble sort algorithm to complete is going to be exactly like that. So all we need is to say, okay, it has a form like this. Are we still doing okay so far? All right. So what do you do when you compare algorithms? So when you compare algorithms, um, we can have bubble sort pit against, say, selection sort. Okay, so when you pit bubble sort against selection sort, the T1 would be different, the T2 would be different, and then the T3 would be different. But it still looks like this. We good so far? All right. What if you are to compare bubble sort against, let's say, merge sort? Merge sort has an n log n complexity. So with merge sort, the time complexity is going to look like this. You have a T1, certain things you have to do exactly n times, and then certain other things you have to do n times log of n times, like that. Okay? And some people may ask, okay, and you'll be right to ask too, are we looking at log of 10 or the natural log or log of 2? It doesn't matter. It does not matter because you can always adjust T3, to account for whatever log you're using. Okay, so that's it's not a big deal. You can use whatever log you want to use here. We just adjust T3 or the scaling of T3 to make it, to make it work. Say that one more time. This is the exact amount of time that it takes to sort an array that is entirely out of order to begin with. Yep. Hmm? Yep. Yep. It's the worst case scenario. You're given an array that is sorted in the opposite way. Yep. So why do we care? Okay, so I'm gonna give you guys a scenario that some of you may encounter. Hopefully none of you will, but you might. Okay. So let's just say that out of college, okay, out of after you get your bachelor's degree, you couldn't find any job, which unfortunately is likely for many people. I'm not saying about people in this class. I'm just saying that in general, it is actually likely to happen. It's more likely to happen than before these days. So I can at least tell you the trend. So you ended up delivering pizza. Okay. Well, I mean, a job is a job. Okay. If you can get free pizza for meals, okay, it's better than nothing. Okay, so let's just say that you pick up this job, you deliver pizza, at least as a side job. Okay, hopefully you'll be in graduate school too, at the same time. So one day your boss, is complaining about how customers do not like their pizza being cold, and people do not make sense when they choose a route to deliver pizzas. Okay, that sounds like something that can happen, right? So you remembering, this class and many other things that you have learned, you go like, oh, boss, I can write you an algorithm. I can basically check out, all the possible routes, okay, and tell you which route is the best. Okay, so let's go through, that particular algorithm. So let's just say that you have, okay, what do you think is a reasonable maximum number of stops for pizza delivery before the car has to go back to the pizza shop? Go ahead. How many? Four, maybe five, right? Because pizza do get cold and and customers don't want to wait for a long time. So we'll just say five, okay? So we have five stops. We start from the pizza shop, right? So we have these five stops A, B, C, D, E. Okay. So now, how many different routes can you think of to go to each stop exactly once and then come back to the pizza shop? Well, let's think about it this way. Okay. How many choices do you have for the first stop? One, two, three, four, five. Okay. So you have five stops to choose as your first stop for a hypothetical route. So once you have chosen the first stop, how many stops can you choose as the second stop? Four, and then three, two, one. Oh, sounds like a permutation kind of thing. It is a permutation thing. It is permutation, not combination. Because a route of, let's say, A, B, C, D, E, okay, may take a certain amount of time. Do you think a route that is going exactly the opposite, E, D, C, B, A, is going to take exactly the same amount of time? No, especially if you live in the city, because there are a lot of one-way streets. Okay, so and also the traffic pattern changes as you go through all these points too, so it is not symmetric. Okay, so we go like, okay, fine, there are 120 possible routes. If you try to work out everything by hand, like trying to put in five destinations or including the pizza shop itself, six destinations in Google navigation, it's going to take you a lot of time to get it done. Okay, but since all of you are smart, you go like, I know how to use Google Maps API. I can just use a program to evaluate all 120 possible routes, pick out the smallest, the one that is that's the shortest, and recommend it to the guy, the person who is going to drive the delivery car. Is that okay? Your boss loves you. Okay, your boss says, everybody's happy. The customers are so happy that the pizza is at least warm by the time they get it, and the person who's doing the driving get back to the pizza shop, early enough to do some other stuff. Okay, maybe to stock the back room and whatnot. Okay, so everybody is happy. You get a promotion. Okay, which usually means they give you a deeper discount if you want to buy pizza from the pizza place that you work for. Okay, cool. And then one day, your boss calls you in and go like, "You're fired." You go like, "What? Just 2 weeks ago, I was the favorite employee. I'm getting all these deep discount on pizza that you guys have left over anyway. So why are you firing now? Why are you firing me now?" The boss says, you embarrassed me." You go like, "What?" The boss said, "Well, I have a friend who works for a delivery company. And when I showcased the program, it worked okay. And then my friend takes a program and then put in all the destinations, and your program does not even come back with anything. It just hung up. You go like, mm, okay, I'm not really sure what's happening here, but let me first get the idea of how many stops are involved with your friend's delivery company. It's not pizza delivery, it's like Amazon or UPS or FedEx and stuff like that. Okay, so what do you think is a normal day with a UPS driver? How many stops? Sorry, 150? Okay, let's just call that 100. You have it easy. Yes. So let's just say we have a really light day. Okay. So let's just say that we only have 100 stops. Okay. You go like 5 versus 100, 20 times. Okay. So what is the big deal? My program, you'll come back with an answer for this one within 3 seconds. So 3 seconds times 20 is a minute. Okay. So you said that the program never come back with an answer. Well, as it turns out, it doesn't work out that way. Because with five stops, you have 120 possible routes. And you have to evaluate every single possible route in order to figure out which one is best, right? What about 100? You have 100 factorial. So what is 100 factorial? Let's let's take a quick look using a spreadsheet because I'm not going to work this one out myself. So the factorial of 100 is calculable. It can be calculated. It is 9.33 something times 10 to the power of 157. Okay, so exactly how long is that? Okay, so let's just say that this is the number of routes, right? And we'll just say that you can process. I mean, this is grossly overestimating. Let's say you can process 100 routes per second. Okay, so using the Google Map API, that's not possible. Okay, I know for sure it's not possible. Okay, so but let's just say that is the case. Okay, so now we divide it by 100. We take this number and say, yeah, let's divide it by 100. Great. The power of 10 just dropped from 157 to 155. So how much time are we talking about? This is in number of seconds, right? So I'm not going to bore you with a lot of details. We just take this number and divide it by 3600. That would be the number of hours, okay? And then we'll look at the number of days divided by 24 hours per day. And then we'll take a look at the number of years, okay? Which is not going to knock too much out of this thing, especially in terms of the order of magnitude, because we only have 365 and a quarter-ish days in a year. So we look at this number and divide it by 365.25. I know it's not exact, but close enough, okay? It will take this many years to complete the whole thing. How old is the universe so far? Let's check out. Let's check it out. Okay, just for the sake of calculation. Um, we go to Gemini. Okay, the what? Do you guys prefer your Grokopedia? Okay, how old is the known universe? Because guess what? We really cannot know the age of the unknown part of the universe. So we'll just say the known part, okay, the part that is visible, observable by telescopes that we have on Earth today. Say again? 13.8 billion. Okay, so how does 13.8 billion compare to the number that we were just looking at here? Nothing. Okay, so in order for the known universe or the stuff that is expanded that we cannot see because the light has not reached us yet, okay? So, but according to that theory, the universe has to be expanding really, really fast for that to happen. Yep, yep. It's called red shift versus blue shift. Yep. Read that stuff. Astronomy is really cool. Yep. We can even tell, whether there's a rocky planet of whatever size that is revolving around a star from the wobbling of the sun. So so a planet revolving around the sun cause the sun itself to wobble a little bit. So the sun itself is doing this very, very slowly, okay, very, very little. But because it's doing this, sometimes it is heading to you, other times it's receding from you. When it's going toward you, it will do a blue shift. When it's moving away from you, it will do a red shift. In other words, the frequency of the marker lines, because of the elements of that makes up the sun, those lines will all shift, kind of like this. Okay, so from the period of that shift, you can kind of predict, how much the sun is wobbling, and also how frequently it's wobbling, and from that you can also deduce the size and the weight of the planets that are going around that particular sun. Yes, it is Doppler. Yep, yep. But in this case, it's not just calculating how far the sun is moving away from us. You're calculating what is along the orbit of that sun. Yep, sort of, because just because it's the right mass. Yep, yep. It has to be in the Goldilocks zone in order for life as we know it to exist. So, but there can be other types of life too. Yep. All right. So let's just say that this is an insane amount of time, and that's why your program seems to have hung up. Is that okay? So what are you going to do? Remember, the premise of this entire discussion is what you know, what I'm going to tell you can save your job. Okay? So what are you going to do to save your job? You just say, oh, you call Tech. Tech knows that I'm a good student, right? Tech GPT. Yep. So, nope, nope, that's not what you're going to do. So, what you're going to do is to use the analysis of the time complexity of algorithms. As it turns out, this is also known as the traveling salesman problem, which is what we call an intractable problem, which means there is no known quick solution. Okay. Well, if you just want a solution, it's easy. Just go for A, B, C, D, E, and you're done. Okay, but if you want the best solution, it is a really, really hard problem. Okay, so chess is not hard. Chess is not hard by comparison. It's not even close. Because the chess tree, which means you make a move, your opponent makes a move, you make a move, your opponent makes a move, that tree is actually not as horrendous as we thought it was. Okay, simply because we have so much computational power now. I mean, your calculator can beat the crap out of you any day with no internet access. Just because we have so much processing resources now, problems that used to be considered AI is now like, oh, it's just an app. Okay. But anyway, getting back to this problem here. So now that you know the term is called intractable, okay, you can now tell your boss, it's like, well, what you're trying to solve is an intractable problem, okay? You can fire me, you can hire somebody else, okay? You can hire the smartest computer science person, but no one can solve this problem to date. Now, does it mean that no problem can solve it in the future? No, but all the smart people all the way up to this point of time could not solve this problem in an efficient way. And those problems also known as P NP complete. Okay, so it's called NP complete. You can look up that term in Wikipedia, Grokpedia, or whatever. Okay, but that term is actually really important. Okay, because it doesn't describe a single problem; it describes a whole classification of problems that are known to be intractable. Okay, so that can potentially save your job because your boss is trying to apply a solution that works for a very small case that works okay, but he's trying to scale it up to a point where it is not possible anymore. It's just not practical. So are we good so far? So that is the reason why we kind of talk about time complexity because that can save your day. Or it can break a day, because you choose the wrong algorithm. So it can go either way, whether you apply that correctly or not. So let me go and kind of go back to here. We're comparing algorithms. So I can give you one more example of the importance of time complexity. This is back in 90, I'm going to call it 93, no, 94. Okay, so we'll call it 94. 1994, that's about 40 years ago. 30 years ago. So I was working on my dissertation using Microsoft Word. Guess the version number. 2.0. Okay, Microsoft Word 2.0, which I think was the first version that runs in Windows, and it was Windows 3.1, maybe 95. I cannot remember. I cannot remember. But anyway, it was a laptop computer that I have, and I was using Microsoft Word. So in the dissertation, you have a lot of cross-referencing. Okay, you put and basically an anchor point, to a certain section, and then you say, okay, see section blah 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 for whatever discussion that needs to go there, right? So initially, the document I could save it just like any document, and it gets longer, noticeably longer and longer. My dissertation was only about 80 pages, which is really short by comparison to any doctoral dissertation in any subject area. So it's not even that long. It is also using 12-point font, double space, so the actual amount of content is not that dense. And then it comes a point when I try to save the file, it wouldn't come back. You can click Control S, and then just the whole system just keeps going and going and going. So at that point, I cannot remember what I did, okay, but I had to choose. I had to change the strategy of how to write my dissertation because the file could not be saved anymore. My suspicion is somebody at Microsoft did not know anything about this and chose an algorithm that is excessively slow to the point that I could not save the file. So whoever wrote that piece of code should be fired. So this is the reason why we have to talk about this, okay? And then once you graduate from here and then you move on to a 4-year university, most likely you will have to take a class called the analysis of algorithms, okay? Or the other way around, which is algorithm analysis, okay? One way or the other. So the only purpose of that class is to come up with a formula that can tell you about how long it takes for an algorithm to complete. Well, actually, I take it back. The first question is whether it will complete first. Because whether a program will terminate is actually the first question. Because if it doesn't terminate, then it doesn't make sense to ask when it is going to terminate. So you will first have to determine whether it's going to terminate. Then you have to calculate when or how long it takes to terminate. When it does terminate, does it give you the right solution? Okay. So that class is all math. Makes this class look like a Mickey Mouse class. That is what you're heading to. Okay. So that's kind of why we have to talk about the concepts, the notations, and whatnot, so that by the time you get to those classes, things are not looking foreign to you anymore. Okay. You understand the terms, you understand the definitions of stuff. You just have to focus on the actual core concepts that your professor will be teaching you in those classes. Is that okay? I just want to put everything into a context so that why we are doing this, and how this is going to be useful, probably about in a few months or maybe a year. So, yes, you mean by measurement or by measurement? Oh, that's easy. Let me. Okay, Okay, so let me show you something that kind of negates the importance of what you're asking. So I'm not saying that your question is not important. I'm saying the answer to that question may not be very important. Okay, so let's go ahead and play a few scenarios. Okay, so I'll give you another story now. All right, so we have Tack and then we have Pat. Okay, so let's just say that a company is downsizing, which is what we are seeing with a lot of tech companies, and it's down to me and Pat competing for the same spot to stay employed with this company. And then the my boss says, "Okay, how about this? We'll settle this with a programming contest." Okay? And I'm just going to give you guys a sorting algorithm as the test. Okay, and we're going to time you. Okay, the boss says I'm going to time how long your algorithm takes to sort this many items and how much time it takes for Pat's computer to solve the same problem. Okay, and then Pat looks at me and go like, "Well, Tech, guess what? This is in my back pocket already. Look at your computer. You started too early here, and they never upgraded your computer. You're still running a 386 computer. And me, on the other hand, is getting a octa-core, top of the line Xeon processor. So I'm just going to beat you regardless of what algorithm I choose to use. We good so far with the setup? Okay. So we are now going to ask Gemini and ask what is the order of magnitude of difference when it comes to the processing speed between a 386 DX computer, which means it's 32-bit wide instead of the really hackish version of the 16-bit version, versus a modern day octa-core processor. Okay, so we'll ask what is the or how do we compare? Okay, how does the processing speed of a 386 DX processor compare to a modern day top of the line AMD 64-bit architecture 40 AMD 64 architecture. So we don't have to name the correct one, because Gemini can figure that out. I just need a rough number. That's all I need. And of course, Gemini is going to go full out to get all the details to give me a very exact, number. Okay, it's hundreds of thousands of times faster. Okay, so we are looking at some estimates here. So combining all of those factors, deeper dive, blah 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 blah. Okay, the, well, since it's already saying hundreds of thousands of times faster, okay, what do you guys want to use as a base number? The clock speed there's no comparison because the 3D6SX only runs at 33 megahertz. Yeah, so I think they took all of those into consideration. So if you just look at MEPS or million instructions per second, we are mm, so per core is 21,000. So when you combine it with other factors, it just says hundreds of thousands of times. Let's call it a million times, okay? So for the sake of this argument, it's 1 million, okay? Okay, so we'll plug that number into our spreadsheet. Okay, so let's just say that I choose um, merge sort, which is n log n, and then Pat decides to use bubble sort, which is n squared. Okay, or better yet, let's turn this sorting into just searching. I think that's a that's a bigger difference. So we'll look at search as an algorithm. So we're going to need a new column. Okay, insert a column to the left, which is n. Okay, what is the problem size? So when the problems, and I'm also going to need a number here, which is 1 million, because that is representing the factor of how fast Pat's computer is compared to mine. So when n is 1, it would take my algorithm a single comparison as opposed to Pat's computer. So because Pat's computer is already this much faster, so it will take 1 unit of time for my computer, and it's going to take Pat's computer exactly 1 divided by this factor over here. Okay, so that's G1, and I'm going to make the G or the 1 um, a dollar so I can use it in other columns. All right, cool. So Pat looks like this and go like, Tech, I just beat you. Okay, so why don't you pack your desk and get ready to leave the company? I go like, wait, 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 let's double the size of the array, okay, and see what happens. So with binary search, it's easier to work with a power of 2 minus 1. So the next power of 2 minus 1 is going to be a 3 because it's 4 minus 1. So in my algorithm, it would take exactly 2 comparison. So with Pat's computer, it's easy to compute. It's whatever this number is, and then divided by this number over here, except I have to, oops, except I have to change the 1, which is the row number, into a dollar sign so it does not move. Okay, so that's kind of important. So now we bumped the size up, okay, because I'm still losing. So Pat is saying, Tag, you're just a sore loser. Okay, so let's keep this on because I don't have a problem. I can keep this up all day long. Or really? Okay, so next one up is 7. So with my computer, it would take exactly 3 comparisons. Pat's computer is completely linear to column A. Okay, so it's going to take this many. This is all relative. Okay, by the way. Okay, so we are not measuring in real time. It's just time. With my computer using one single comparison as a baseline. All right, so I can now work on this one. Oh, looks like the current number is 2 times the previous number plus 1. Remember what we said about noticing patterns? That's the pattern that I'm noticing here. So we can say, oh, okay, so we can just multiply this by 2, add a 1. Ah, looks at this. This is 2 to the power of 4 minus 1. So if that is the case, I just need to add 1 to the number that is on top on my row, and then this one is already done. So now I have a pattern, okay, as a spreadsheet. So we go like, okay, so tag, you're still losing by a whole lot. So we can actually look at the factor too. So if you look at the factor, it is basically my time divided by Pat's time. So he or she, I chose Pat for a reason. So he or she was basically beating me by a million times, and now it's down to 266,000-ish. Okay. So it looks like I'm gaining. So you keep going a little bit more, okay? So at that point, your Pat is going like, ooh, I don't like this anymore. I go like, oh, let's keep going. Ugh, tech is catching up clearly because the gain is no longer a million times. It is now only 36 times, okay? And we can keep going, okay? So it's like, oh, okay. At some point, it crossed over already. The last time Pat was winning, it was when the problem size or the array size was about 16 million. Let's call it 7 million. Once I double that, it crossed over. Pat's computer is now slower compared to mine, even though mine is a really old archaic computer that is running a million times slower than Pat's computer to begin with. So that means if you choose the wrong algorithm because of the wrong complexity or a lesser complexity, there's no saving. Okay, you can have the faster computer hardware, more RAM, more resources, and in the end, it will still lose out. The only point you're changing is at what problem size is going to cross over. The crossover is a certainty. Is that important? Is that okay? All right. Now, if you're comparing selection sort versus bubble sort, then it's just a constant. So the faster computer definitely wins. Okay, but if you're comparing a log and algorithm, which is binary search, versus a linear algorithm, which is linear search, the difference is huge. So I'll be doing okay so far in terms of the importance of understanding time complexity. No, it's just log n without the n. Quicksort is over, the average is n log n. In fact, the same class about, the analysis of algorithm class, they will show you that um, there are no algorithms, no sorting algorithm can be faster than n log n. That's it. If you have found a n log n sorting algorithm, you're done because there it does a faster algorithm cannot exist. Yes. Yep. Yes. Okay. So with the remaining 5 minutes, I will tie this class in with Cisp 310, assembly language programming. So let's just talk about merge sort. Okay, there are two implementations of merge sort. One is recursive and one is non-recursive. Okay, so the recursive one basically says, okay, I'll break this array into two. You sort this half, you sort this half. And then of each half, it will go like, okay, how about you sort this half and you sort this half, and so on. So by the time you get to an array with only two items, do you need to break down any further? No, because with only two items, either they're already in order or you just have to swap them. Then they become in order. So then you go back, okay? So when you go back, you kind of have to merge, the two arrays on each side of the tree, and it becomes bigger, and then it becomes bigger and bigger. So from that perspective, it is really easy to clear. It's easy to see why it is n log n, okay? The iterative approach is a little bit different. So in that case, you can imagine you have three tapes on those really old mainframe computers. You start with a tape that has all the data to begin with, and then the first split will split it into two different tapes. But the nice thing about this is the tape that is being read is only moving in one direction. The tapes that are being written to also move only in one direction. Okay? And then when the split is done, you do the merge. The merge is kind of the same thing. The two tapes that you were writing to, they become the tapes being read, and then the tape that was being read before is the tape that you're writing to. But once again, it's only in one direction. Okay, so as opposed to you're splitting an array into two, and then you split into two, you split into two, because by the time you get all the way down to the leaf nodes, you are there's no continuity. Okay, you're not reading memory in a sequential way. Okay, so this all has to do with whether you're reading or writing to memory in a sequential way. Why does it matter? What is DDR2 or DDR3, DDR4 or 5? Double data rate. Okay, DDR is double data rate. How does it work? Well, the way it works, or the reason why it works, is because in order to address a location in RAM, especially DRAM, it takes a long time. Okay, and that's why you have to insert actual wait states. Once the processor says, I need to access that location, and that address is sent out of the processor, the RAM component needs a lot of time to say, okay, let me go sort out the thing. This is on this page, and on that page, this is at this location. Okay, now I bring this content back to the data bus to present the actual data. It takes a long time. Okay, so how does DDR work? DDR basically says, okay, how about this? I just tell you once where I want to start reading, and then for all the subsequent memory clocks, you just give me the content of the following location. So now the addressing, the slow part, only happens once. And then after that, for every single clock of your memory bus, it can give you the content of the next location and the next location and the next location. It's very good for burst mode reading of an entire block of memory. When we talk about the block, we are talking about 128 bytes, 256, maybe 512 bytes. Okay, so it's not gigantic. Is that okay so far? So with the iterative version of merge sort, okay, you are reading in, let's say, 128 bytes, but you are reading all 128 of the 128 bytes that you have just read into the cache, and you're using all of those. So you're making full utilization of the DDR whatever number technology. On the other hand, the recursive version of merge sort is from the memory access perspective, it's all kind of random location because of the way we split the array into smaller and smaller halves. So that means, you spend all this time to read 128 bytes in, of which you're going to go like, yeah, we're going to take a look at these 16 bytes, and then out of the 128 bytes that you read, 16 bytes are read, and then the rest is useless. Okay, so that means that algorithm, along with quicksort, which is even worse, okay, is not making use of the DDR technology because DDR is only super duper useful when you're doing sequential access in memory, block type sequential access. So to answer the question that was asked earlier, it does make a difference. Two algorithms can both be n log n. If one is making full utilization of the hardware speedup, the other one cannot utilize the speedup. The one that makes use of the speedup can still be significantly faster compared to the other one. No, it won't change the complexity, so the shape of the curve would still be the same, but then you have a proportional difference between the shape. So one may look like this, the other one is shallower like this. But it's kind of like a compressed version of the one that is the full height. Hmm? They're still different. Yes. So when it comes to that, there's no catching up. The faster one will always be faster. Correct. Yeah. But when people consider, what algorithm to use, sometimes they have to take the architecture into consideration because it can make a huge difference. Yeah. Yep. All right, we're out of time today. I'll see you all on Wednesday. Don't forget it is your exam too, okay? And we are changing the policy, those bathroom break, during the exam. So measure your water retention time. Sorry?